In this video, let us discuss about single-phase transformer. Before studying what is single-phase transformer, we need to know what is Faraday's law of electromagnetic induction. We need to know self-induction, how self-induced EMF is developed. We need to know what is mutual induction and how mutually induced EMF is developed, and why we call a transformer as a static device. And then we'll see into the principle of operation of single-phase transformer, the two types, step up and step down transformer, and the types of transformers based on its construction. So this is the schematic diagram of a transformer. You can see the transformer is submerged or immersed in transformer oil, and it is kept into this tank, right? And why we do that? Because there are losses in a transformer. There are losses in a transformer, right? So these losses are in the form of heat, and the heat is absorbed by this transformer oil. And another one more thing is this oil gives insulation to the transformer. Right? How does this heated oil get cooled? So we have a cooling system here. We have cooling fans, and this hot oil goes into this fins or these tubes, and then returns back. Because you all know that hot oil goes up and the cold oil comes down. We have an oil pump. If it is a very big transformer, we need to circulate this oil. So there are cooling fans to push the air inside and cool the oil. Another two important things in this schematic diagram is the conservator tank. The conservator tank, uh, there is oil filled 3/4 in this conservator tank. The two purposes are there. One, if there is a heat rise inside this oil, it becomes bubbling, and if you do not stop it, the tank gets bursted, right? So in order for that excess oil to move to some place, we are providing a conservator tank. Another one thing is, if this oil uh, gets evaporated, right, due to course of time, so some oil needs to be filled into this tank, so we are having a conservator tank. So we have oil level gauge which will show the level of the oil that has to be present there. We have a Buchholz relay, that is a protective relay, which shows which cuts off the supply when there is any short circuit that takes place, and it acts as a protective relay. We have a dehydrating breather here. See, the upper part of this conservator has air, so it has to be without moisture. So we have silica gel here, and the moisture air gets into this, and the silica gel removes all that air, and dry air is inside this conservator. So you can see a real photo of the high power transformer here in the left hand side. So what is Faraday's law? Whenever a conductor is placed in a varying magnetic field, an electromotive force is induced. If the conductor circuit is closed, a current is induced, which is called induced current. So when you see this diagram, this is the core, right? Uh, there is a conductor in the primary side, there is a conductor in the secondary side. This is called as primary coil and secondary coil, right? So when a AC supply is given to the primary, so alternating flux is there. So this alternating flux travels through this core as well as through the air, and it cuts the secondary winding. So our thing here is, we need a conductor which is cutting the magnetic flux, or the magnetic flux which is cutting the conductor. In our case here, the magnetic flux cuts the conductor. If it cuts the own conductor, it is called as self-induction. Right? So how Faraday's law works in this? See, when the flux lines cut the secondary of this transformer, the power from the primary is transferred to the secondary without any electrical connection, but is transferred through magnetic flux lines. So this is how Faraday's law helps or in the transformer working. So next we'll see what is self-induction. So there is a primary coil and there is a secondary coil. So if the in any conductor, if the current flows, there is magnetic flux lines, and if it cuts the same conductor, right? You can see coil 1, EMF is induced. That is called as a self-induced EMF or due to self-induction. There are magnetic flux lines which will cut the secondary coil, right? If it cuts the secondary coil, you can see that EMF is induced in the secondary coil, and if you provide a closed path, current is flowing in the secondary side. So all the power from the primary side is transferred to the secondary side here. So this is the basic of a transformer. Right? Next, you can see that why it is called as a static device, because there are no moving parts like a generator or motor, but it uses the principle of electromagnetic induction. Okay. A transformer operates on the principle of electromagnetic induction. It has a magnetic core. It has two sets of winding, primary side and secondary side. When one of the windings is connected to the AC supply, so you can see here V1, an induced EMF, that is E1, self-induced EMF, and these flux lines cut the secondary, and this is called as mutually induced EMF E2, and thereby a current I2 flows. And if you are connected a load, right, so you can see that the power has transferred from the primary side to the secondary side without any electrical connection, and we are having a core to enhance the magnetic flux lines cutting. So you can see the definition of a transformer. You can see the definition of a transformer. A transformer is defined as a static electrical device that transfers electrical energy from one circuit to another through the process of electromagnetic induction without change in frequency. So generally it is commonly used for step up or step down purposes. Right? We'll see it in the coming slides. So what is step up transformer? So as we know, the voltage is directly proportional to the number of windings. So you can see here, if the number of windings in the secondary side are more, the voltage is obviously going to be more, right? So the input side, the windings are less, so less voltage. Output, the windings are more, number of turns. Right? So this is called as a step up transformer. What is a step down transformer? So we have more number of turns in the primary and less number of turns in the secondary side. So obviously the voltage is going to be lesser than the input side. Right? So we are calling it as a step down transformer. Next we'll see what is an auto transformer. See, in auto transformer we have a single winding which is acting as the primary side and the secondary side. Right? So the only thing what we are going to do in the auto transformer is we have tappings in the secondary side. Right? As I already told you, if the number of turns is varied, the voltage is also going to vary, right? So if in this first tapping, so if we are giving 230 volt in the primary side, so here if you are keeping the um, wiper or that arm in the first tapping, the number of turns are less, so the voltage is also going to be less. When you keep it in the second tapping, the voltage is going to increase. Right? Similarly, the variable voltage, for example, if you have given 0 to 230 in the primary side, you can get from 0 to 230, you can vary at the output. So step up, step down, and auto transformers. These are the various types of transformers. And based on its construction, we can see that in the coming slides. So one question I want to ask you, can a transformer be given DC? No, it cannot be given. Why? Because it is designed only for AC. Why it is designed only for AC? See, since it works on the principle of electromagnetic induction, there should be a change of flux, right? So change of flux is taking place only in the case of AC supply. So what happens if we give a DC? So if we give a DC, there is constant current which creates a zero induced EMF. Right? So as a result, what will happen is the transformer primary will behave like a short circuit, and hence heavy current will flow through the primary and which in turn will burn the windings. So next we'll see the different types of transformers based on its construction. So we have three types: core type, shell type, berry type. When you see core type, uh, you have a laminated core. We can use E type or L type or I type. In the case of core type transformer, we are using L type channels. Why these laminations are used? Because we need to reduce the eddy current. And in between these laminations, you have insulations, right? So see, you can see as we normally have seen in the uh, theory that the primary winding is in another side and the secondary winding is in other side, but practically it is not so. What they do is they keep both the primary and the secondary in the same limb. Why is it done so? Because the magnetic flux linkage has to be more, right? So as you can see, you can see the dark blue circle here, right, in the below diagram. That is the low voltage winding, and the light blue color is the high voltage winding. So what is this yellow color ring? That is the insulation, right? So both the primary and the secondary winding are placed in the same arm. Right? So here the winding surrounds the core, so it is called as core type transformer. Right? What is shell type transformer? In the shell type transformer, we are placing both the high voltage winding and the low voltage winding, or otherwise called the primary and secondary, are placed in the middle limb, as you can see. So, what are the laminations that are used here? E type laminations and I type laminations are used here. Right? So, here the core surrounds the winding, so it is called as a shell type transformer. Right? Next, we'll see what is a berry type transformer. Right? We'll see what is berry type transformer. In a berry type transformer, we have several core, right? In the, as you can see here, and it forms a middle limb. In the middle limb, similar to a core type or a shell type, we are placing cylindrical windings. We are placing cylindrical windings, right, in the middle limb. So here the low voltage winding is placed, and after that a lamination is placed, and then the secondary winding is placed. So this is the berry type transformer, right? So as you can see in this slide, the left hand side is your core type construction with low voltage which is placed near the core. Why do you place the low voltage core winding near the core? So that the insulation can be lessened, right? If you place a high voltage, you need to provide large insulation, right? Similarly, in a shell type also, you are placing both the low voltage winding and the high voltage winding, and you can see the different types of laminations. So L type laminations, U type laminations, I type, E type. Why these laminations are used? See, and they are placed opposite to each other when they are stacked, right? So to reduce the magnetic leakage, right? So these are about the different types of transformers based on their construction. So I have taken some references from the net. Right? So thank you for watching this video. Hope you have understood what is the basic of transformer and the various types and the operating principle of a transformer.